Welcome back, engineering students. Whether you're in mechanical, civil, or gearing up for industrial maintenance, mastering statics is literally your golden ticket. I am so excited to be your virtual mentor today as we walk through this step-by-step explainer. Consider this your ultimate no-nonsense guide to mastering rigid body equilibrium. We're going to bridge that tricky gap between your final exam equations and real-world heavy machinery. So let's get those concepts to actually click, shall we? Okay, let's dive into this. Here is our roadmap for today. First, we'll cover core 2D principles, then jump into a quiz on roof frame analysis. After that, we'll look at an industrial application with tractor mechanics, followed by a tractor free body diagram quiz. Finally, we'll tackle 3D equilibrium principles and wrap up with a final exam summary.
Let's kick things off with Section 1, Core 2D Principles.
Okay, so to keep any two-dimensional structure in equilibrium, the math just has to balance perfectly. It's a strict rule. The sum of all forces in the x and y directions plus the sum of all moments absolutely must equal 0. But here's the crucial constraint you have to remember. In 2D, you can only solve for a maximum of 3 unknowns. Now, you can replace equations, like swapping out a force equation for a moment equation, but you can never, ever augment them to find a fourth variable. If you overestimate your unknowns in the real world, well, that's exactly how you get catastrophic mechanical failures.
Moving right along to Section 2, Quiz, Roof Frame Analysis. All right, let's put that fresh knowledge to the test. Imagine a structural frame supporting part of a building's roof. Try to vividly visualize the physical load here. We've got 4 separate 20 kilonewton forces pushing straight down on this horizontal beam. Meanwhile, there's this massive cable running over a pulley and anchored securely down below, and it's pulling back with a known tension of 150 kilonewtons. Just imagine the sheer structural stress building up in that main joint as these opposing forces battling it out in 2D space.
So here is the question for you. Which free body diagram is the most correct for this roof frame? I want you to literally pause for a second and try to visualize it, or maybe sketch it out on some scrap paper if you have some nearby. Remember, getting your free body diagram right is the make or break step. If your diagram is flawed, your math is going to be flawed too. Let's look at our options.
Taking a look at option A, notice how it cuts the cable at the pulley and just throws a 150 kilonewton vector in there? Plus, the main support is totally missing the necessary reaction forces for a fixed support. Option B, on the other hand, correctly represents the external reactions at that support. It calculates an X force, a Y force, and a moment. It also accurately leaves that entire cable intact right down to the anchor point, showing us the full 150 kilonewton tension vector.
Now let's check out the remaining ones. Option D is just fundamentally incorrect. It represents the anchor completely wrong, basically treating it like a solid block reaction instead of a dynamic cable under tension. But look at option C. This one actually holds some technical merit. It cuts the cable, sure, but it accurately calculates the 150 kilonewton tension forces acting on both the pulley and the beam.
So the crucial point is, option B is the absolute most correct free body diagram here. It perfectly isolates the entire frame and cable system while showing the right support reactions. Now, option C is actually acceptable depending on exactly how you isolate the system, but options A and D, those are conceptually flawed and they will absolutely cost you points on an exam.
Let's lock in this strategy. Step 1. Always create a comprehensive free body diagram for your frame and cable. Step 2. Apply your equilibrium equations. That means setting the sum of forces in X to 0, sum of forces in Y to 0, and sum of moments to 0. Do that and you'll systematically solve for your reaction force components and the moment at your fixed support. Let's jump to Section 3. Industrial application, tractor mechanics. Now, let's pivot from static buildings to some heavy-duty industrial machinery. Picture this massive loader roaring to life on a busy job site. When this tractor lifts a heavy bucket of earth, those forces don't just magically disappear, right? They transfer directly through the frame, dynamically shifting some really intense physical loads across the front and rear axles. As an industry engineer, you need the spatial awareness to calculate the exact ground reactions at those tires so the axle doesn't literally snap under the pressure. Now, what's really interesting about this specific problem setup is the units. You might notice pounds and inches, but for the sake of our specific calculation rules today, we're strictly treating the LB units as newtons and the inches as meters. So think of it as a 2,100 newton tractor lifting 900 newtons of gravel. Our ultimate goal? Determine the exact ground reactions at the rear wheels and the front wheels.
To conquer this, you need to follow a strict, non-negotiable three-step process. Step 1, create a precise free body diagram of the tractor. Step 2, apply your equilibrium conditions to generate your three equations. Step 3, solve the math for your desired quantities. You really need to know this sequence by heart.
Moving to Section 4, Quiz, Tractor Free Body Diagram. Let's see you apply that process. Which free body diagram correctly represents this 2100 Newton tractor lifting 900 newtons of gravel? I want you to carefully evaluate the reaction forces at the front and rear wheels. Pay super close attention to the tractor's center of gravity, marked as G, and look at where the load is applied, out there at the bucket. In problems like this, the direction of your arrows means absolutely everything. Let's compare the first two. Option A shows the 2100 Newton weight of the machine and the 900 Newton gravel load pointing straight down, while the ground reactions are pointing up. Option B, however, shows the rear wheel reaction force pointing down into the ground. Which of these correctly maps to physical reality? And looking at options C and D, we can easily spot some subtle directional errors. Option C has both weight vectors pointing down, but inexplicably has the front wheel reaction pointing down as well. Option D makes a similar mistake by pointing the rear wheel reaction down. Just think about it realistically. The ground pushes up on the tires to keep this heavy machine from sinking into the earth. Yes, option A is for sure the correct answer. It accurately places that 900 Newton load and the 2100 Newton weight pulling downward, exactly in opposition to the upward normal ground reactions at both sets of wheels. This perfectly visualizes the mechanical equilibrium required for that heavy tractor to operate safely. Let's move to Section 5 and see how this builds into something bigger: 3D equilibrium principles. Take a look at this X, Y, and Z coordinate system. Now, this isn't just a basic sketch. This 3D axis is literally the mathematical scaffold you must project onto complex industrial connections in your mind. When heavy machinery operates in real 3D space, forces don't just push down. They twist, they shear, and they pull across all three planes at the exact same time. So this is where we really upgrade your engineering toolkit. Jumping into 3D equilibrium, the complexity scales up significantly. Instead of just 3 equations, you now require 6 scalar equations. That's the sum of forces across X, Y, and Z, plus the sum of moments across X, Y, and Z. And because you have those 6 equations, you can now solve for a maximum of 6 unknowns at your various supports and connections. And this brilliantly illustrates our final takeaway in Section 6. Here is your ultimate cheat sheet summary for acing those final exams. For 2D problems, you have a maximum of 3 equations and 3 unknowns. For 3D problems, it's 6 equations and 6 unknowns. And the golden rule: always begin by drawing an accurate free body diagram. If you get the visual representation right, the math naturally follows. As we wrap up this explainer, I want you to look up from your screen. Look at the structures around you right now. The chair you're sitting in, the ceiling above you, the heavy vehicles outside. What hidden forces and invisible math are keeping them in perfect equilibrium at this very second? Keep analyzing, keep questioning how the world is held together, and you'll be an incredible engineer. Thanks for hanging out with me today, and I'll catch you in the next one.